Hello, everyone. Welcome to the last technical webinar of the Human DeFi Hack. During the last 2 weeks, we have held 10 webinars. So we would like to thank you for attending this marathon of webinars. And today, to put the cherry on top, we have the pleasure of counting again with Filip Piwowarski, who will give a deep dive about two of the main components and two of the main parts of a stack of a DeFi project, as they are oracles that, don't forget, in Eternity, they are built into the protocol, and also the fungible tokens according to the AEX 9 standard that is native to Eternity. So thanks a lot for coming to the webinars. We hope you have enjoyed them. You have them on YouTube available for any when you want to see them. And yeah, I will leave it you with the oracles and AX9 masters, Filip, also known as Piwo. Please, Filip, come onto the stage. Welcome. Thanks again. Let's start.
Hi, thank you. Welcome, everybody. Let me share my screen. Okay, as Alex already introduced, I'm going to talk today about two very important components in the Eternity ecosystem. First, the oracles, which are native to the protocol, as you have maybe heard. And second, the AEX9 standard, which is a fungible token standard similar to ERC20. Alex, can you mute yourself?
I'm
okay.
muted.
Somebody else was typing. Okay. Let's start with the Oracle system. So the Oracle system is native to the Eternity protocol, meaning they are separate transactions in the Eternity blockchain that will form the Oracle system. They provide a concept of trusted oracles, meaning if there's data provided in the oracles, you will have to either build upon these to make a non-trusted version, for example, with proof of fraud system, for example, or multiple oracles, as we do in Superhero itself, or you simply trust a centralized data source, and these oracles can provide real-world data to the blockchain and to a smart contract, therefore. And these oracles can incentivize the operator. Anybody in Eternity, any key can operate an oracle, and they can can generate funds using this. One example would be, for the oracle system would be the New York Stock Exchange could run an oracle, for example, where you can get the current price for any stock on the stock exchange. As the data itself is generated by the New York Stock Exchange, you would trust their data source anyway. And of course, all of the data is put into the blockchain using signed messages, so we can verify that the key used is in fact their key. But the data source, or what the data says, we will just have to trust the provider of the data, the operator. For each data set that is provided, the person that needs it has to pay a fee to access it. For example, the New York Stock Exchange publishes the price of let's say, Eternity tokens. If they would list them, you can query, please, New York Stock Exchange, give me the current price of Eternity tokens, and pay the fee together with this transaction. And once they give you an answer for this query, they will receive this fee, so they can generate some income with this. Of course, operators can also provide data for free. Let's go over this in a little bit more detail. So the life cycle of an oracle would be: the oracle operator has to register an oracle. What does this mean? They have to make a transaction where they say, what's the query and response format, so that an automated system, for example, your smart contract can read this data. They have to provide the fee, the amount that is to be paid by the account that queries for a response of the oracle, and a time to live has to be specified, the time for the oracle to be alive on chain. Operating oracles that are alive for a longer time are more costly. Having short oracles are less costly, but in general, it's very cheap in transaction fee, just to prevent spamming. And one caveat is that you are only allowed to operate one oracle per account, but of course you can generate as many accounts as you want, as the oracle address will equal the account address. So the account will be the provider of this oracle. Then somebody wants to receive data from the oracle, meaning the oracle has to be queried by the user or by the smart contract of the user or by an user of an app. So anybody can do a query to any oracle in the blockchain. There's no limitations for this. And they have to provide a query in the format as specified by the oracle operator. The oracle operator set a fee that has to be included. So the one doing this transaction has to pay that fee. Otherwise, the query will not work and be rejected by the blockchain to pay the operator. But they can first check, is this fee, am I willing to pay this fee or not? In our use cases, we use the fee for the operator for the account to not run out of balance, as to provide a response, the operator will have to make a response transaction, paying a fee to the miners of the blockchain, and we shift that fee to the user so that the oracle always has funds available. And then the oracle query also has to specify a time to live for the query plus for the response. So a query will not stay in the blockchain forever, and the response will neither, as this would spam the blockchain, but it is there for, let's say, 20 blocks, 1 hour, or 2 hours, or 10 hours, or 2 weeks. You can specify any time to live, I think, up to 2 months or something like this. 50,000 blocks, I think, is the theoretic maximum. And the fee for the blockchain is higher the longer you want the data to be available. But the usual use case is you query and very fast, the response is expected in a very quick way, and then you process the response also very quickly. The next step in the lifecycle would then be the response, meaning the oracle operator has to observe the blockchain for queries towards his oracle. You can poll for new queries in a set time frame, so every 1 minute or so, or you can set up something, a WebSocket listener, for example, to listen to queries happening in the blockchain. The query then has to be answered using an oracle response transaction with the format that was specified when registering the oracle. And you provide, again, time to live for the response, how long the data should be available, similar to the query for the user or for the blockchain to not get spammed. Afterwards, the data will be removed from the state of the blockchain. While submitting this transaction with a response, the query fee is unlocked, paying the operator after the response has been sent. The balance is available. So you always have to start with a little balance in order to register and get your first response. Afterwards, the oracle can be self-sufficient, paying or getting paid by the queries itself. The response will be in the state of the blockchain until this time to live runs out. This also means that if a query has been done by anybody else, the data or the response can also be seen by anybody else for free. So once a query has been done and the data is still available in the blockchain, anybody can see it and has access to it. For example, if the price for Eternity to Bitcoin is very important for a lot of people, only one person has to do the query and response thing, and anybody can access it. And then there's the last step in the life cycle. The Oracle operator can extend the Oracle time to live at any time. So you can pay a fee and keep your Oracle alive, even if your time to live that you initially specified is running out. So usually this would be done. We choose a time to live, for example, 500 blocks, meaning about, I think, a few hours. And then after a few hours, we just extend our Oracle to stay alive, or I think multiple days. And this is the usual way you go about it. And I will show 2 examples. Actually, first, we're going to talk about the Oracle price feed example that I created that you can also access on GitHub. And I will walk you through how we can create an Oracle using the JavaScript SDK, how we can query that Oracle using JavaScript, how we can be the Oracle operator, and how this data can be used from a smart contract. So in the price feed example, as I said, this is the Oracle operator side implemented using the JavaScript SDK and open source in my GitHub profile. And also on the Eternity GitHub, of course. So first that we do is I have this wrapper, the price feed Oracle class that we initialize, then we register our Oracle to the chain, and then we start polling. Let's go into registering. So first we check, is our Oracle, the key pair that we specified, already an Oracle or not? If it's not an Oracle, we're gonna register a new Oracle, which we do with client register Oracle. And here we specify the format that we want to have. In JavaScript, we are bound to primitive types of Sophia. So here we can do string and string, for example, very simple types. But if you work with smart contracts, you can also use any type that is available in Sophia smart contracts, of course. Then, so we provide the query and the response format, which is both string here, and the query fee, and the time to live. So we say a delta of time to live. This is a constant here, or a variable in this implementation. And this is a promise, so we await for it to be returned. Then we can log out the ID of our Oracle. And here I just start an extend if needed. So an interval that just checks every fifth of our time to live. Does our Oracle need extending? If so, we extend it. So let's start our Oracle up, and you see what happens when this register method is called. So our Oracle client is initialized with the time to live of 500 and auto extend true. So this auto extend logic will run. The Oracle is created under the ID. So the address of the Oracle is OK_2PJA. It checks if the Oracle needs extending, which it probably doesn't. And it starts the polling right away. And it also says to us, no need to extend the Oracle. We are still within our time to live. Then this is the extend if needed logic, where I just check out, do I have to extend my Oracle with the current height? If not, if so, we do use our Oracle object that we assigned here where we said this oracle is register oracle or get oracle object using the address of the oracle. Then we extend the oracle again by the time to live and replace our oracle object with this. And afterwards, as I said, we started polling. So we listen for or ask the blockchain, are there any queries for our oracle present? If so, as we do this using oracle.poll queries, where we give a function that will be called when there's a query incoming. And we pass an interval. Here I just used 2000 for every 2 seconds we check it, which is quite frequent. And then the response function gets past the queries. Here I just sort for the latest query, just to have one query, and check for the empty response, just a fail-safe mechanism that we do to not get stuck here. Then we can decrypt using base 64 our query string. We log it out to our console. And in this oracle provides an API for the CoinGecko API to get the price of eternity for any currency that is provided in the query. And this data is fetched using the CoinGecko API here. And if we got a response, we will respond to our oracle using oracle respond to query using the query ID, passing the price of eternity in the selected currency, and getting the response, giving it a TTL of 20 blocks. This is all of the logic that's needed in JavaScript in order to be an oracle operator. And as I said, this is also open source, and there can be, of course, you can do any kind of logic here, even manual, that a user will come and input some data, check any API, provide any other data that you wish for here. Or you can also wrap it. All of these functions are also available as smart contracts. So this kind of logic can also be done by a smart contract automatically. And then also here are some, in the repository are some examples on how to access the data using Sophia. So let's check it out. I'm gonna copy the Oracle address that my Oracle has been registered with, and this is running and checking all the times for queries towards my Oracle. Let's go in the editor that I already used, where I pasted in the query for eternity price. So we see here it has a method in it where we have to specify our oracle that we want to query during initialization of the contract. And it has two functions: query the price of eternity in a given currency. It checks for the fee, checks if the fee is paid, checks if the length is 3, as every currency pair, for example, BTC or ETH for Ethereum, is 3 letters in the CoinGecko API that we check in JavaScript then. And we check if the oracle is existing. So if it's not run out of TTL, for example, or if there's any other mistake with it, because then we cannot use it. And these checks are just here for fail-safe and to give nice error messages. We don't require them if the user does everything correctly or your app does everything correctly. You can just skip those. And then we call oracle.query. We pass our oracle that we have in state, pass the currency, pass the fee that our oracle has, and give the same query and response timeout of 20. And the second function that we have is a check query, where we can get the answer if it has been answered. Let's compile this contract and deploy it. As I said, I will pass the oracle identifier as an argument to the init function. Let's deploy it. And it's deployed now. And let's call the function query AE price. And we want to get the AE price in Bitcoin. So I pass BTC as an argument. Let's call the function, and it will fail now as I have not provided any fee. And here it will say amount not equal fee. And this is the fee in Atto that I have to pay, so smallest unit of eternity. I put this in together with my query, call it again, and now it will work. And it gives us the result, which is the reference to the query that was just created. I'm gonna copy this now, and we can see in our JavaScript example, the Oracle got the query for BTC, and the Oracle will respond with this value from the CoinGecko API. Go back to our editor. Let's use the check query function, pass our query here, and call it, and we now see the result in our smart contract. We can do this programmatically and then use the result for any calculation that we may wish. Here it's just as an example, a string, but you can, of course, do any other data type. This is the first example that I wanted to show. And all of this is here in the GitHub repository, where there's some information on to do hosting using Docker, for example, how to use the hosted version, some example that I'm running all the time on mainnet that you can just check the price of eternity if everything works as you expect without running your own Oracle, and how to use the SDK example to query the data as well, which I'm not going into right now. And of course, as I said, in Superhero, we are also using oracles. What we do in Superhero is we have multiple oracles. So independent contributors, community people run oracles. Right now, there's, I think, 7 or 8 oracles running that are listening for people using Superhero and their queries. And what we want to have here is, if 50% of the oracles agree on what the response is, then we say this is data we trust. As greater 50% of oracles say the same result. In Superhero, we use this to claim tokens that were tipped towards an URL, where the query is the URL and the response is the address that the token should go to, that the individual oracles will then be able to check. So what do we do here? When we query an oracle in Superhero, we estimate the fee because we have to check if the fee is correct. Our estimate fee function will check all of the fees for all of the oracles that we currently know and sum it up, because we have to satisfy all of the fees, of course. We check, are the fees matching that have been passed together with this query or not? Then we build the query that we have. As I said, we query the expected account and the URL. So we pass string.concat, expected account, semicolon, and the URL. And then what I do is I define a function here. I define a function with our oracle where we say oracle.query the oracle with a query string, giving it the fee and our TTLs as we had in the previous example. And then for all of our checked oracles, where we check each oracle before calling it if it's available, query this oracle and save the queries that we had. And we store these queries in the state of the contract, so we can go and check back later, have these queries been answered with the here per URL, we store all of these queries. So we can go and check back. For this URL, have there been queries answered? If yes, in the future. When we want to do this check in Superhero, what we do is we have this function check persist claim that does some checks. Has this URL already been verified? If yes, just return the old example. If no, run the check, where we run our function check claim again with the URL and the account. What does check claim do? We pass the URL and the account, and we check for Oracle answers. I will go later into this. This checks all of the answers. We check the list of the answered. Is it greater the minimum that we require? We require a minimum of 3 answers right now, or I think 4 answers right now. And then we match these answers to their response. Are they positive or not? So is the account matched or not? And if we don't have didn't get an answer, we assume it's not positive. And here we just check what's the percentage of accounts that has given a positive answer. If our percentage is greater 50%, as I said, we assume it was successful, or the check of the oracles was successful. We remove our queries, of course, to clean up in our contract state that we don't have to store all the unnecessary data, and return our success here. And this will then be stored as well in our contract. And the check of Oracle answers just maps, does list comprehension in Sophia to go through all of the Oracle queries that we have in our state for this URL and get the answer of the query if the Oracle is alive. Oh, yeah, here. Whoops, here. And it will check, is the response the same address that we expected when originally calling the smart contract. So this is how we use oracles in Superhero, and this way anybody can use oracles in a more decentralized way, requiring many answers. If it's 10 or 5 or 500, does not matter. Either you trust the data or you think of a system as we do here with multiple oracles that have to agree on the response to build an oracle system. So with this, I am finished with the parts about oracles, and we will continue with fungible tokens. Are there any questions about oracles so far?
Yeah, Jet had 2 questions. The first one is there a default value for the oracle fee and TTL, if not specified, that extends the oracle automatically?
No, there's no default values for fee and TTL. You have to specify them yourself, because the operator and the user that queries for the data are the only ones to know what is your life cycle. For example, for the TTL, I know that some human has to react in order to give the data. Like, if the query is what's the mood of Jet, and you want to make some decisions based on this in your smart contract, then you have to be awake and type in the result yourself, probably, and you will not be able to react within 1 hour, because sometimes you sleep for 8 hours a day. And then you will have to set the TTLs way longer, and only you know this, so there's no default there. In Superhero, we use 20 blocks as a TTL, as it's a good minimum, where we have some time in order to react, like 1 hour for everything to be okay, and to check for the results. But it's not persisted forever, so we can save in fees. And the same with the fee, 20 blocks we use in Superhero right now, yes. And the same with the fee. You can provide your data for free and pay for the transactions yourself if you wish to. Or you can say, my data is very valuable. You have to pay me 10 eternity for each response. And then the user can think for himself, is it worth to query that oracle, to pay that fee for this response? Do I really need the data or not? So you can look for yourself. In Superhero, what we use is a default fee that pays for all of the responses. So only a very small overhead is generated in fee so that the oracles can continue operation forever. But you could also think of setting a higher fee, for example, to pay for your server costs. And the second question was, can an oracle be used as an API that gets responses from either a native database or another smart contract state object? With an oracle, you can use any API or any data source. It does not matter. You can, as you've seen, the query comes in Sophia smart contract, so you can query another smart contract if you wish, or you can use in any programming language, receive the data, and it doesn't even have to happen automatically. As I said, if you want to query for your mood, a human can input the data manually, or you can write API that accesses your database if you think this is really needed. But for accessing another smart contract state, I would use a remote contract call, as it's a lot simpler. Just query this on-chain is very much simpler as doing Oracle response and a query and response. Carlos asked, how does it look like when behind an Oracle is an actual human? So, as I had in my example, in the Oracle price feed, here with the response, we automatically check the CoinGecko API. But here we can do anything and just wait for it for a very long time. Here we can go ahead and say, human goes and does things and inputs the data later on in the same system, and then the response will be sent. It doesn't matter if there's 1 second timeout, us querying the API, or a human getting in here, checking what's the query on his screen, query for Bitcoin, and then goes somewhere and puts in the response all inside of here. And of course, this is not the only way you can do it. This can, of course, also be split into 2 parts, where you go later, 1 hour or 10 hours or a few days later, and put in the response if you've seen there was a query. Are there any other questions for oracles on Eternity?
There's another question from Jets. He asked, does this mean the fees paid to an Oracle address can be transferred to another public key?
Yes. The Oracle is just, an Oracle is registered for an account, as I showed in the first slide. So if the Oracle generates fees, so let's say the Oracle receives a fee for each query of 10 tokens, and you only have to pay 1 token in fee, you generate an overhead of 9 tokens per query. And this accumulates all the time in the account of the Oracle, and you can spend this to any other account in Eternity, of course. Yes, the Oracle is an address just as the contract has an address. An Oracle, a contract, everything are just things that have an account in the Eternity blockchain. With a contract, it is you create a contract, and with this, create a new account for it. With the Oracle, it is you have an account and you register it as an Oracle operator. Any other questions? Let's wait for a few minutes if somebody else wants to type their question. Yes, any account can be registered as an Oracle account, but you can just have one account, one Oracle per account. So if you want to have multiple Oracles operating at the same time, you need to create multiple accounts. With what the work we do, we assume to just create a new account for any Oracle that we want to operate to separate these things. So we create a new account, then register the Oracle for this and give it a small fee, a small balance to start work with.
I have a maybe not so technical question. What kind of oracles did you personally implement, let's say, in smart contracts or for any applications?
So as I said, we use oracles in Superhero that I and the Superhero team implemented. That what they do is you provide a URL. Then we have a parser that opens this website in a Chrome browser and checks for the content of the website and reports this data back to the blockchain if this address is present there. And we run some scripts on it. For example, in Superhero, when you want to check or tip a tweet, a URL of a tweet, then we don't only check is this public key present in the tweet, but we also go to the profile of the one that has tweeted and check in their bio if this address is there, and then report this back with the Oracle response. And the other thing that we've done is, for example, these price feeds where just price data or exchange data for Eternity token is provided using this Oracle price feed. Omar asks, what's not recommended to do with an Oracle? I would not do user interaction with it, as it has a lot of overhead, for example, and this can be done way simpler with simple contract calls. If you just need your user to execute some logic in your smart contract or put in data in your smart contract, just have it given an endpoint, make him call it from your app and use smart contracts for it. Or don't provide any private data that only yourself are allowed to access, that's not public info or should not be public information, should not be put in an Oracle, as all of the data in oracles are public. Of course, what you can do is you can locally encrypt and locally decrypt somewhere else with a known key. The question then is, what's the benefit of using a blockchain? Maybe you have a benefit, then it's fine. If you have a set of parties that is interested in receiving and paying for private data on the blockchain, yeah. And as Eric says, never share your private keys, of course. Any other questions towards oracles? Omar asks, do you know what oracles are out there? Of course, you can go to the node and check if there's oracles, and you can just query them if you pay their fee and see what they do. Or central parties can advertise the oracle. For example, if I'm an exchange and I provide exchange data and want people to use my data in their smart contracts, I can say, here's my oracle. This is the address. This is the fee. Call it at any time, and I will give you the data. Or as we do in Superhero, where we do these checks with ourselves, this can be thought of. Or anybody can build as you said, we could build an Oracle marketplace. Yeah, on other blockchains, there are Oracle marketplaces available where people can register the Oracle and make this into a registry, for example, and say, here's an Oracle that gives this data in this format if you pay this fee, as like a marketplace for oracles. Of course, this can be done by anybody. Just an aggregator for this data. Okay, then let's continue with fungible tokens. So AEX 9 is a standard. AEX stands for Eternity Extension Protocol, where we extend the Eternity standard with additional standards, for example, in smart contracts or in interaction on the Eternity blockchain. With AEX 9, we created a standard for fungible tokens. Our goal with AEX 9 was to be very similar in the interface to ERC20 on Ethereum, as a lot of people are familiar with ERC20, and we wanted familiar use case and functionality, and also familiar interface for developers, that they can integrate AEX 9 quickly. We wanted to create a minimal token standard, so not a lot of features, everything that's needed to make fungible tokens work, though. We tried to learn from all of the mistakes that were done on Ethereum. With ERC20, there were some bugs, for example, the allowance bug, where exchanges or some other parties can cheat people using allowances, or some issues where front running can happen using allowances. And this was learned from, and the interface is different in AEX 9 to ERC20 there to work around this problem. And AEX 9 can be extensible. So anybody can change the smart contract and add other extensions or make a standard for a new extension if needed. We find the Eternity fungible token here under Milan's GitHub. Let's jump into there. What will we find here? We will find our AEX 9 definition with a simple summary. So fungible token standard on Eternity. What's the motivation? We want to have very simple functions for transfer and balance. And we provide two implementations. First is the basic token. This has a set of methods. The first is the AEX 9 extensions is the first method that has to be defined in the AEX 9 standard. It gives a list of string for each extension that is implemented in this token. In the basic token that has no extensions implemented, this is an empty list. We report this as a list of strings for applications to show a different interface if other extensions are implemented. You will see this later on. Then we have a function that returns meta information. So any information that is not logically relevant, but can be used by applications to show information about this token. This includes the name of the token, the symbol of the token, and the decimal places as specified as an integer. So any decimal place can be shown. Then there's a function that returns the total supply. So what amount of tokens is the total supply of this contract? Then there's a balances function that returns all balances that are available in the fungible token. This is a map of addresses to integers. So each account to the balance of fungible tokens will be returned using this function. Then there's a separate balance function where you have to provide the address as an argument, and it returns an option of balance. We return an option here as we want to indicate if the user has no or never had an account with this fungible token, then the return value is none. If it's if the owner has a balance, even if it is 0, it will be returned sum 0 or sum of the balance that this address, the specified address, has. Then there's a function to do a transfer, where from the caller's account, we transfer to an account a value of tokens and return nothing. All transfers transfers of 0 value must also be treated as normal transfers. We don't ever check for 0 values here. They must be treated as normal. And there's also a transfer event that must be fired by an implementation using the AEX 9 standard. And this is all that is there in our basic token. You have balances and you have transfers. And there's a certain set of event. This is just the transfers. And then there's extensions. As I said earlier, the function AEX 9 extensions has to return a list of implemented extensions as a list of strings. For example, mintable. If we want our token to be minted by somebody, we have to implement mintable, and our AEX 9 extension function has then to return also mintable. So any application that knows how to mint tokens can use this mint function according to the mintable extension as standardized. And then we also have to, of course, provide the mint function. Minting means creating new tokens for an account out of nowhere. So we provide the account and the value of tokens that should be minted. And here, there's no checks done, but you can, of course, implement your own logic inside of this mint function to say there's a cap, only 10 tokens can be minted. If 10 tokens have already been minted, then it doesn't work, or provide a wide list of accounts that can be minted towards. In our standard implementation, we assume that only the owner can mint tokens and nobody else can mint tokens. And the mint event must be fired so that, for example, a block explorer can then show there have been tokens minted using this mint extension. There's the extension burnable, which has to be defined as burnable string in the AEX 9 extensions method. So we define burn. This destroys this amount of tokens from the caller. So anybody who calls this function with a value greater than 0 will destroy tokens in the AEX 9 standard. Also here, the burn event has to be fired. In ERC20, we have allowances, so we have a extension allowances also has to be specified as the string allowances in the AEX 9 extensions method, where you have multiple functions now. What an allowance is, you allow another account to take a certain set and a certain number of tokens out of your account. So you give an allowance towards another account, and then they can take money out. For example, if you want to deposit funds with a decentralized exchange, you would use an allowance where you say, the decentralized exchange can use 100 of my tokens at any time. This is a deposit then. And they can make a transfer or call a function with the tokens in the name of your account. And at any point in time, you can remove or change this allowance. So first you have to create an allowance for an account with a value. This value can be anything. It can also be greater than the balance you have. Of course, then any transfer will fail. Then there's the transfer allowance function, where the other account can transfer tokens from your account if your allowance was given from account to account a certain value. And you can check, is there, what's the list of allowances for my account? Where you pass the allowance and it gives you the value that is allowed. You can check for all allowances in the fungible tokens and just what's the allowance for the caller. So how much am I allowed to spend from this account? And then there's, of course, the change allowance function where you pass, if you want to change your allowance for account, this account that you created the allowance for, and the value change. This can be a positive or a negative value. If my allowance is 100 that I created, and I only want the allowance to be 10, I have to value change minus 90. So I change it from 100 minus 90 to 10. And I can do this with any amount if it's greater than 0. Negative allowances are not possible, of course. And I can reset the allowance to 0 at any point in time using the reset allowance function, just to not have to do multiple calls to set it to 0. And there has to be the event implemented allowance from account, for account, and the value. Then there's the extension swappable. This is can be used to swap an AEX9 token for another token on the Eternity blockchain, for example, or for future native tokens on Eternity or other AEX9 tokens, for example. The swap function here is a very generic function that we don't have, that we specified the interface for, but there's no default implementation, as we don't know what you should want to swap for and what your custom logic will be. But what it does, it burns the whole balance of the caller and stores the same amount in a map so that later it can be checked, for example, in another contract, what should be minted there. There's a check swap function if this has been swapped already. And there's a swapped function that returns all of the swapped tokens. And it must trigger an event for the swap, of course. And there's a reference implementation for the token out there. Also, you can find this together with tests in the repository, where you find here the fungible token AES. This is the basic token implementation, as I said, with a lot of comments inside. So every line that we have here is commented what happens within this line. So if you have any things that you don't know what happens here, you can just check this. And it's very simple. It's only 118 lines for the basic token. And we have a full token implemented that, as you see here, implements allowances, mintable, burnable, and swappable. All of the functions are implemented here. And also, again, a lot of comments here to know explain you what's happening in the public interface. So that's the basic overview over the AEX9 standard. And I will show you an example of how to use it in order to create a simple token sale. So here, this is a sample application for a token sale on Eternity. The price of each of our SCT sample test token is 10 etto. So 10 smallest eternity. If you pay those, you will receive one of our sample test token. So if I enter an amount here, for example, I want to buy 42 SCT, the price will be 420 etto. Let's click the button and it will say to me, I transfer roughly 1 euro cent and will receive, which is 42 pico A, so 420 ettos. Let's confirm this. What it does is it calls a token sale function, which then mints tokens for my account and keeps track of all the balances. So now I see this account just bought 42 of the tokens. And of course, I can just choose any other account. Let's copy our address, go back to our initial account. Oops, let's reload quickly. Okay, it's broken now. I don't know why. I probably closed the server, but I can, of course, transfer tokens to another account, which I cannot show right now. Let's jump into an example here as well, how this is done in code. So we created a token sale contract. This has an owner, a price, and the token. The token is a reference to our remote contract, which is a fungible token, as I just explained, that implements the mint function, mint address int returning unit. When we initialize our token sale, we have no token set yet. We have our owner, which is the call caller, and the price. And then we deploy our fungible token contract. In our fungible token contract, we set the owner of the fungible token contract to this contract, and then we can set the fungible token contract here, which means this token sale contract is allowed to mint tokens. Then, when the contribute function is called by somebody using our token sale application, we check is the token set. If so, calculate the amount, which is the call value divided by the price, as we said earlier. For 420 etto, you receive 42 STT. So we divide by 10. And then we take our token and call token.mint this thing. This is the basics of our token sale. And of course, there's a function where the owner of this token sale can withdraw all of the balance. So here we check, we spend to the owner our balance of this token sale. So these tokens have been sold. You receive some AEX9 token for some Eternity tokens, and the creator of the token sale can pay them out to himself, of course. And in JavaScript, this looks like this. When we open the token sale, as we've just seen, we check our address, what's the balance. We check in our token contract methods balance, we check what's the balance. And then show it, where I've seen earlier 0, and then after I bought some 42. The contribute is also very simple. We say our eternity, our token sale, we call with contribute. We pass the correct amount and price times the price, so the correct thing that we want to buy. And this executes, and then we refresh our view to show the new balance. And the transfer is also very simple, where we call our token contract method transfer with the address it should transfer to and the amount it should transfer. So this is a very simple use case for a token sale using the AEX9 standard. Are there any questions for fungible tokens on Eternity?
I just posted a question, or Jet, go ahead.
Is AES mentioned early the same token that's used by JellySwap? I don't know what token JellySwap uses, to be honest.
Because they also have a stablecoin called AES, so I was just wondering if they're using just the same reference implementation that was in this AX9 GitHub repo, or if it's just a coincidence that it just also called it the same. But I guess we'd need to ask JellySwap.
we don't call it the same.
Because
Their
I've
token
seen
is Eternity Stable, AES for Eternity Stable, and ours is AEX for Eternity Extension.
But I'm sure I've seen also AES somewhere in your presentation before.
You've seen AES as the file name of our smart contract,
okay.
which is Eternity Sophia, so AES.
Sure, sorry, I was confused.
Yeah, no worries. I don't know what standard they use. You will have to ask the JellySwap team for that.
Okay. Jet wanted to ask something?
Any question from you, Jet, or any other questions? How is the current market of fungible tokens, example stablecoins? So as mentioned, there is the stablecoin from the JellySwap team. I don't know what's the state of it, to be honest. And the standard is public. The AX9 standard is public. Anybody can use it. And with the future release of Superhero, it will also be integrated there for tipping and creation of new tokens. But of course, it's open. It's been there for 1 year. Anybody can make a token sale, for example, for their project. There's nothing that's keeping you back. And Emmanuel, we cannot hear you. Yes, you can create tokens very easy using the wallet extension. And this functionality will also come to Superhero Wallet, also with showing your balances for different tokens soon. If one creates a token with that method, how can one use a smart contract to transfer mint from the token? Exactly as I've shown in the tokens in the token sale example. Here we call token.mint, just do a remote contract call towards our token contract from the owner. And the same with transfer, it would be token.transfer the address. This is an example from the smart contract side. And of course, you can call the transfer function also from JavaScript in your user application with the transfer method here. But one does not get the contract of the token. Here, we set the contract of the token in our token sale. So we set the token. Here, token is some token that has been passed by the owner of the contract. And then we can call token.mint in our application. We initialized, when starting up our app, our token contract and our token sale with the address as instance in JavaScript.
Sorry, can we hear me?
Yeah, now
yes.
Okay, cool. What I was trying to ask is, if one deploys a token using that wallet extension, one does not get the contract to that deployed token.
I have not used the wallet extension to do so. If you deploy it using the SDK or a contract editor, you will always receive it in return. And
you would always receive the contract code for the token?
I don't know the wallet extension very well. You will have to ask the team that builds it, but I think that it's also deprecated in favor of Superhero Wallet in the future, which will, of course, give you the address.
Okay, cool. Thanks.
I have a question. If it is very cheap to create new tokens now through Superhero or through the wallet extension, is it likely that the Eternity blockchain will be spammed just like the Ethereum blockchain was spammed with CryptoKitties?
So it is very cheap to create tokens. You only have to provide the source code, and it's not that big. And the Eternity virtual machine is very efficient, so it's very cheap to do so. There's no additional fees to create a token because it's just another smart contract, and we want to make it cheap for anybody to use it. Spam is only in the eye of people that consider something spam.
Yeah, I mean, in the sense that chain would get overloaded like from too many token creations at the same time.
So Eternity itself is about 3 times more efficient as the EVM, and plus there's about 4 or 5 to 10 times more capacity in general in terms of transactions per second. So even if there would be CryptoKitties, we can handle 10, 30 times the amount of transactions in theory.
Okay, perfect.
So
yeah, now we should
try
put
to make their applications, and nobody has done that yet. But feel free to do so. We would be happy to have lots of token transfers. Is there a way to show your AEX9 source code contract for a third party to check? Asked Omar. Of course, there's. You can always give your implementation of the fungible token to anybody else, and they can check, does it match the standard, for example? We only trust the standard because this has been tested very well. And you can give the bytecode, you can check the bytecode with the compiler version and see if it matches up with your implemented version that you're calling, and be sure you only call trusted AEX9 implementations. And in some cases, for example, in the governance app, we do this kind of verification as well. But usually, for ESD20, it is the case that a lot of people make their own implementations, and you will have to check every implementation because they want to make custom logic, for example, in their token sale, a maximum cap of tokens that can be minted or something like this. But we recommend, if you make a token sale, don't do it in the actual fungible token standard. Do it in a separate contract as we did here, because then it's fully compliant with the standard, and all of your custom logic can be somewhere else. Are there any other questions for this? I will later share, of course, the slides with you, and also the links that I've shown you and the reference implementation for all of the Oracle examples, how it's done in the price feed example with its documentation, how we use it in Superhero, as well as the token sale example, and the link to the fungible token standard will be in there, of course. Yes, the link will be in the thing, but I can also share here the list of the repository, and there you will also find the full implementation.
Philip, are you here?
Oh yeah, sorry, I was muted.
Okay.
So here we find in the repository under contracts and then fungible token full, you will find the source code of the fungible token. Full implementation, but you should only use the extensions that you really need. For example, if you don't want the admin to create an unlimited supply of tokens, by minting tokens, you should probably not have the mint function inside. As a user, I would not want to use a token where the admin of it can create any amount for himself or inflate the supply at any point in time. Omar asks, out of context, but what do you think about NFTs, non-fungible tokens? So the AEX9 standard is the implementation for ERC20 style fungible tokens. There can be a similar thing with non-fungible tokens. For example, ERC721 re-implemented similar as we did with AEX9 on Aeternity, where we try to learn from some of the mistakes that have been done in the past and not make them on Aeternity again, while keeping a very similar interface for non-fungible tokens. This can be done. I think one of the Aeternity Starfleet teams has created such tokens already. I'm not sure if they are open source, though. But I think non-fungible tokens are great for their use cases. So if there's no further questions, I think that's it from my side.
I have two more questions that I forgot to ask before about Oracle, sorry.
Yeah, go ahead.
So I asked, can state channels interact with oracles off-chain? This was a question that I heard like a long time before, and I still didn't understand very well how it works.
Yes. If you have a state channel, you can access any Oracle data that's on-chain if both parties agree for the access of on-chain data. You cannot access off-chain oracles on-chain, of course. And the second question of yours was, is it difficult to create a reputation system based on oracles using smart contracts? Technically, it's not difficult, no. You just have to find good rules for a reputation system.
But you would write it in the smart contract, not in the Oracle, right? Like you would...
Yes, your reputation calculation has to happen in the smart contract.
Okay.
And then your oracles can be scored or whatever by this reputation. Okay, if there's any further questions, feel free to also ping me in the forum and I will answer them there, or have a look through the provided resources in the slides. Thank you very much, everybody.
Thank you, Philip. It was really great.
Awesome, Philip. Yeah, I'm not quite confident that there is no questions, because I guess there is a lots of questions, but probably they didn't pop up yet. So we're in the Discord channel, Telegram, and Eternity forum to solve any questions that you might have to master oracles and AEX9 tokens. So this said, and as always, thanks everyone for attending this webinar. It will be available together with the presentation in Devpost, and also we will make it like publicly available after the hackathon. So yeah, this is coming to an end. Now it's time to start brainstorming with your teams, starting coding, and we start the action now. So we can't really wait to see what will be going on, and all the team of the Human DeFi Hack, all the mentors and so on, will be happy to support you in anything that you might need. Thanks for all our amazing lecturers, Piwo, Milen, Nikita, of course, Omar, the people that participated in the AMA, and the biggest thanks to you all participants that you are striving to build awesome projects in this hackathon. Thanks a lot. We will be in touch. Some more sessions, but more relaxed about networking and dApps will be scheduled. We will keep you updated. And yeah, that's it from my side. If anyone of the team or participants have any other remark, please go ahead. Thank you. It seems not. So thank you very much again. Have a wonderful day. Bye-bye.
Thank you, everyone.